To begin with the steps taken in our project, we first take a look at problem formulation and data collection. Breast cancer is a prevalent and potentially fatal disease that affects millions worldwide. The earlier it's detected, the better the prognosis. But how do we improve early detection? That is the issue we aim to solve. Our goal is to create a model that predicts whether a tumor is benign or malignant with high accuracy, harnessing the predictive power of machine learning. And for this, we turn to data. Our dataset is a Wisconsin Diagnostic breast cancer dataset available on Kaggle. It comprises features computed from a fine needle aspirate of breast masses, detailing characteristics of the cell nuclei. We have radius measurements, texture, perimeter, area, smoothness, and many more, each providing a glimpse into the cellular world of breast tissue. Now, why machine learning? With a rich dataset at our disposal, machine learning can discern patterns far too complex for the human eye. It's not just about the volume of data, but also about capturing those subtle nuances that differentiate malignant from benign. This is a binary classification problem, one of the most common yet vital types in machine learning. Our model will output one of two classes, predicting malignant or benign, aiding clinicians in diagnosis. The significance of this problem can't be overstated. By providing an accurate early diagnosis, we can open the door to timely treatment, potentially saving lives.
Okay, moving to pre-processing and visualization, we first load the dataset and examine statistics and informations. Here we see that we were fortunate that there were no missing values or null values in the dataset, so we did not have to take additional steps to normalize the data. We also see that all the feature variables are continuous and only diagnosis, which is the target variable, is in categorical type. Furthermore, the feature dataset were divided to three subcategories, which are mean, standard errors, and worst values, which are indicated as numerical values here. One as in the mean values, two standard errors, and three worst values. Then we are ready to use the dataset for pre-processing. We first set feature variables to X and target variables to Y. Okay, and here we then examine the statistics and information. Then we normalize the values, so each features is in the same scale when we feed it to a neutral network. This helps for numerical stabilities within the network. Okay. First, we created the overlapping histograms, as you see here, and parallel coordinates, a diagram that you will see later, of the mean feature variables to show that the feature provided can indeed be viable as a predictor of malignancy. It is to check whether the patterns and relationships exist within the dataset that a model can perhaps learn. In these figures, we generated two histograms of certain feature filtered as malignant and then the other as benign. Green as in the benign and red as malignant. Less overlaps means that it has better predictability of a value for malignancy. So if you compare this radius 1 and texture 1, it is shown that radius 1 has more predictability. And here is the parallel coordinates to compare the score types. We did this for the mean and the worst. This is parallel coordinates for the mean. And here we created a histogram for the standard error and worst values as well. So these are standard errors. And we go to the worst values. Okay. This is the parallel coordinates of worst values. Um, Visually speaking, in terms of the ability in classifying between either M or B, worst values shows comparably better than the other parallel coordinates. Um, it is be said that this pattern is logical enough to conduct model based on this.
Hello, so for model training and evaluation, this is how our group did it. So first we need a list of the different Python libraries to be used. So this is in the requirements.txt file. Next is to actually import the necessary libraries to be used. Then we use the CUDA for our device. So this is restricted to NVIDIA GPUs, and this basically just checks if it's available, else we use the CPU for model training. We then fetch the dataset, split the data into features and targets, and just check the metadata of the dataset itself. Now, what percentage of the data should be training, validation, and test? So we do not have any validation set, and training data is 80% of the whole dataset, while test data is 20%. The split was randomized by using the sklearn.model_selection.trainTestSplit, which randomizes the split itself. So the code implements a deep learning algorithm, specifically a type of an artificial neural network called a multilayer perceptron. We chose this as it is well suited for deep learning architectures for classification tasks like breast cancer diagnosis. The stacked layers with nonlinear activation functions enable the model to learn complex relationships between the features and the diagnosis. Now, for our metrics, we chose balanced accuracy in order to check how well the model predicts breast cancer. We noted that the slight unevenness in the distribution of the positive and negative classes in our dataset, hence also in both the train and test splits, so it can be seen here. And sklearn's balanced accuracy factors that. So after training for 50 epochs, we then evaluated the model on the test dataset through a data loader. The model returned an accuracy score of 0.9792 or 97.92%. Now, what does this mean? Well, an accuracy of 97.92% is a good sign for breast cancer diagnosis model. This means that the model was able to correctly classify nearly all of the data points in the dataset. We also noted from the confusion matrix that 2 positive cases were labeled as negatives. In other words, these are false negatives. We surmised that these were early stage tumors and can be hard to accurately classify as a positive.
Alright, so now we'll be showcasing the fourth part of the project, which is to demonstrate an API call. We're going to do that first, and then I'll explain how the pipeline works. So first, I'm going to run the API. Good. So the API is now running at localhost at port 8000. And we can use Thunder client from VS Code to make an API call. Sorry, I can close this. Okay, so some data here has already been preloaded, so let's try to send it using a post request to this endpoint predict. So it says here it's been right? So this is taken from the test dataset. You can grab another one, for example, this one. Let's see what it says. And so you can try to cover error scenarios, like for example, one of the features is missing. See, it says here, number of features missing 30. What if one of them is text, text that's not parsable to integer? Oops. Yeah, it says here, input should be a valid number and able to parse string as a number. Okay. Okay, so now we'll be discussing how the entire pipeline works. So I'll be taking your attention to the first here, the README file. So these are the packages used. Install dependencies here. It's not going to install this specific version, so it won't overwrite any previous installations. We also want to use unicorn. And then we'll create the model using this script, which will create a model.pth file. Then we can run the web server. If you're using unicorn, here's the command to use. And here it says, there we go, to make an API call, make a post request to predict with a body like the following, where features is an array of 30 raw feature values. Such a call should return a diagnosis like the following: M for malignant and B for benign. So what occurs in create model should have been discussed already, but basically if the data set has, for example, been changed, there's rows that's been removed or edited or added, then the model performance and the test set should differ, of course, especially constrained on made up data, for instance. And okay, so how does it make a prediction? I'll show you. Okay, so there we go. Makes a prediction by running an evaluation call. See the model recently, I'll be making an evaluation call to the model, and then it just returns that prediction in a JSON object. This in the endpoint predict. So what's the benefit of using this sort of machine learning method? Well, the benefit of it is that we have an automated way of performing the task of tumor detection. By leveraging patterns in the data, it simulates the way a doctor's eye might detect malignancy of a tumor, except the features of the tumor are encoded using a precise instrument into text. Assuming one can produce state-of-the-art, such a model might even surpass human ability, which is not a foreign concept to contemporary models experts create today. And yeah, I guess that's it. That's for our presentation.